Screen. So last time we talked about the different spectrochemical measurements and how this instrument is being set up. So usually everyone has these specific components that you have with the control system, the one taking over all the parts of the spectrochemical instrument. So the way that you're going to have it here, you have your analytical sample being introduced through a sample introduction system where, okay, it is converted to a spectrochemical encoder, okay, that changes the concentration into some sort of optical signal, okay, and the optical signal will be converted to electrical signal that is related to whatever's the concentration, and then out of that, they will be able to process the number that comes here, okay, to relate to the concentration of the sample that is being what we call analyzed. So we look at the different what we call optical density there. We focus more on the radiometric system compared to the photometric system during that time. Okay, but if you're going to look at this, there are usually similar. Okay, if you're going to compare the photometric and radiometric quantities, so I think when you say radiometric, it's more on the radiant energy or radiation, while if it's a photometric, it's more on the luminous. Okay, but in terms of quantity, I mean, in terms of the description, they're almost what we call the same. Okay. So we started with the classification of spectrochemical methods, that emission, absorption, luminescence, scattering, and the indirect what we call method. And all of them, as we could see, just involves the radiometric methods. Okay, and we discuss about what is happening in each of these method. Okay. And I think we ended up with, if I'm not mistaken here, the scattering. Okay, so we ended up with this Brillouin scattering and Raman scattering. Okay, so when you say Brillouin scattering, it's just from the reflection of radiant energy waves by thermal sound waves. Okay, while Raman scattering involves the gain or loss of a vibrational quantum of energy by molecules. So after we're done with the book, okay, I think we have 6 chapters. So I'm thinking of finishing 1 chapter a week. So we will be done with chapter 2, and then maybe you can read, okay, the chapter because I think we go on until chapter 6, and then after that, okay, it will be open references. I mean, I will not just base the discussion based on the Engel and Crouch book. I will use the other what we call references. Now, in all of the things that we have, okay, we could say that the selection step, okay, is the one that will allow us to separate the analyte optical signal that we will have. So I would say in all spectrochemical analysis, okay, the analytical procedures involving analytical, I mean, in every chemical methods involving analytical procedure that made use of spectrochemical method, the selection step allow us to separate the analyte optical signal from the majority of the potential interfering optical signals. So what does it mean? We have to find, okay, a way wherein we are only going to measure, okay, the signal coming from the analyte. Okay, so the vast majority of analytical techniques select the desired information based only on its wavelength. So if ever, okay, you have what we call the sample, and you're looking for a certain analyte, okay, your main goal is at least find the wavelength, okay? So when you pass it through a wavelength, it will just give you the signal coming from your analyte. Thus, we could say here, the selection of wavelength is very important, okay? So this is true in all spectrochemical method. So if we're going to look at this spectrochemical method, usually this is how the part of the instrument looks like. Okay, you will always find here some sort of a selector, okay, that will narrow down any broadband sources of light that you have. So if you're going to look at this thing, so this is the instrumentation for spatial dispersion and detection of optical signal. So you can narrow down, okay, at the beginning of the analysis or before you hit what we call your sample, or you can look at it at the end, okay? So it's just like the sample is at the middle in this analysis. So when you look at this thing here, so this is the spectrochemical encoder that usually is the light source. So what do you have here? Usually you have here your radiation, or we could say the light source. Okay, so some of the radiation from this spectrochemical encoder enters, okay, this so-called entrance slits. And what happened here? Okay, it strikes the dispersing element. So there's a dispersing element here, and you can have what we call an image transfer system. So the dispersing element that you have here, the dispersion element and the image transfer cause each wavelength to strike, okay, a different position of the focal point. So some of them will hit here, some of them will hit here, some of them will hit here. Now, according to the photodetector, okay, configuration, you can have various names based on this, what we call optical devices. So if you're going to look at here, when the dispersion element and the image transfer system causes each wavelength to strike, okay, a different position in the focal plane, okay, there's a different photodetector configurations that you can use. Okay, you can use it through this one, or this one. So what's the difference that you have here? Okay, here you might have an aperture, and what you have here is a photographic film or plate or array detector. Now, on the other hand, okay, you can have here an exit slit and a photodetector. Okay, and on the third setup that you have here, you can have several exit slits and some photodetectors. So whatever setup that you have here, it will give you different story. So it's up to you. What is the one that you're looking for? Are you looking for information that can be provided by this, or one that provided by this, or this one? Now, in most instances, you can only get one information. But later on, with the advent of technology and instrument upgrades, sometimes you can get all of them, okay, at the same reading. Okay, so here comes some of the terms that will come up. Okay? Ito yung mga photographic plate, ano pwedeng tawagin nyo nandito, ano yung tawagin nyo nandito, or what you can call on this one. Okay, so I don't know if this is first time you hear the word. Okay, usually you have spectrograph, spectroscope, spectrometer, tapos meron pang ano pang spec. Aside from dyan, graph, scope, tsaka meter, tapos minsan meron pang ano, spectrogram. Okay? So if we're going to look at this one, ano bang ibig sabihin ng tinatawag natin spectrograph. So if you base it from here, okay, we could say that it's a large aperture in the focal plane that allows a wide range of wavelengths to strike a spatially sensitive detector such as the photographic plate. Okay? So pwede yan yung una dito. Okay? So in this case, you have some sort of spectrograph. Okay? So if you're going to look at the spectrograph, usually what? An apparatus for photographing or otherwise recording spectra. Okay? So parang ano lang yan, yung nakikita mo dito, okay, nire-record lang niya yung photograph na nakukuha mo or yung spectra if you have an array detector. In recent year, what happened? Some solid-state video type detectors have become available and are often employed in spectrographs in place of the film. Imagine yourself if they collect still it but by film. Okay? So wala na tayong ganun. Even I think the first Raman that they have, they use like a film to collect that thing. Okay? And if you're going to look at these detectors, they are usually what? May word dito eh. I think in this one. Yan. Okay? Usually, this type of detectors are actually what? An array of large number of closely spaced miniature photoelectric detectors. Okay? Now, ngayon, we could say, ang ano na nito ngayon, eh yung, if you have this PDA, photodiode array. Okay? So, they have the advantage, okay? This type of what we call the detector, they have the advantage that the spectrum can be obtained immediately without the time required for film development. So, imagine if you have the film. So usually it is the spectrograph that you have there, it will be recorded in the film like this. Okay. But because of the advent, okay, advances in technological advances, wala nang, you don't need the film. Okay. You can already obtain the density of the lines that recorded. So yun yung, we could say yung spectrograph. Okay. Now, the other one that we have here, after the spectrograph, meron tayong tinatawag na spectroscope. Okay. So how is it what we call the different from the spectrograph that we have? So if we have spectroscope. So if we're going to look at the spectroscope, this is the device that measures, okay, the spectrum of light. Okay, so this is a device that allows a visual observation of the spectrum. So it is a spectrograph that uses a viewing screen for observing the spectrum in a focal plane. Okay. Saan nyo nagamit to? I'm not sure if we use this in Gen Chem there. Usually, ang experiment ito yung parang ito yung spectroscope. Tapos, andito yung light source. Let's say lamp. And then you try to get the line spectra of a particular element. Okay? Yun yung, we could say, spectroscope. Okay? It is a spectrograph that uses a viewing screen for observing the spectrum in a focal point. Okay, so we could say this is already an advanced, more advanced than a spectrograph. Okay? Now, ano naman yung tinatawag nating spectrogram? As a physics, meron silang ganun. Kasi dito, meron kaming experiments sa Chem. Okay? About that. And we discuss it whenever we have this, ano ba yun? Yung kay Bohr model. Okay? Ano naman yung spectrogram before we go with the last one? Kasi yan yung mga spectro. But if you're talking about spectro, usually, spectro is usually has something to do with light. Okay? But if you have a spectrogram, narinig nyo na ba yung spectrogram?
Ayun ba yung parang output? Parang synonymous sa chromatogram? Hindi pa ba?
Spectral lang tawag natin dito. but that's a good one. Okay? But when we're talking about spectrogram, okay, you only use it to what we call represent the signal strength. Okay? You rarely use it. Okay? But if you're going to look at the definition of what we call spectrogram, it's a visual way of representing, may term silang ginagamit, loudness. Okay? Or we could say visual way of representing the strength of the signal or signal strength. I don't know you know it, but usually they said yung signal na generate natin is just noise. Okay? Now, the only thing that you have to make sure is the noise that you get is from the sample, because there are also some noise coming from the background. Pero yun na lang yung tinatawag na, but when we're talking about noise, usually these are the signal coming from maybe the instrument when it's analyzing without anything, or some other materials that may affect. Okay. So they don't use the spectrogram because it will be confusing. Okay? Because you're talking about loudness. So when you're talking about loudness, nandyan yung noise. But noise now is just associated to any background signal. Okay? So usually, what's your goal? If you try to develop a method or analytical method, make sure that the signal that you have is at least 3 times the noise that generated by the method or the instrument that you use. And if you want to quantify it, because the 3 times is just what? LOD. But if you want to determine the LOQ, how many times it should be then the noise? Anyone?
10 times, sir.
Di ba LOD is 3 times? So ang LOQ ay
10 times.
10 times. Okay? Minsan problematic yung noise. Yung experience namin dito, okay? In Raman, we always has this noise. I'm not sure yung tinatawag namin cosmic rays. So nakakakuha usually siya ng cosmic rays. Now, how do we determine that if it's a noise? If the signal is a noise or the signal is coming from your sample, how do you do that? Anong gagawin nyo? Let's say nakakuha kayo ng signal. Tapos you want to determine kung totoo ba yun or just a noise. Anyone? We always encounter it, lalo na pag laser yung ginagamit namin. So we want it to be sensitive as much as possible. But out of time, may lumalabas talaga yan. So how do you think we overcome that type of signal? Natingin nyo. Okay? You just need to do more readings. You just get your signal several times. Now, if ever in the next several readings you don't see it, then that's noise. And when you average it, usually it will go down. Okay? So yan yung one way na ginagawa natin. We remember, when you're doing Raman, the ship is very important. A ship of one wave number can be say is significant. But what if your own signal ship on its own? I remember, because what we usually do is we always get the reading of the toluene. So the toluene will give us a sharp peak around 10,000 wave number. So after 5 years of working in the lab, we found out that there's a ship. Okay, so let's say in 2011, it's around 1003. And then in 2018, it's around 1008. So the way that we're going to do this is, if this is the background signal that we have, all we need to do, every reading that we have, kung ano yung sample namin, isasubtract dito. Kung ano yung sample namin, isasubtract dito. So to see if the ship is insignificant. Okay, because we thought we discovered something. Oh, laki ng ship. Okay, we thought we have a ship around 10 wave number. And then we realize it's just 5 wave number, but still it is significant. And what do you think is the culprit? Why we have that signal? Okay, so the building is near the Long Island Railroad. So the noise coming from that, even though we have a vibrational table, I think is enough to distract us. But to make sure we're consistent, every time we do a reading, on the day that we do a reading, we always run, okay, a standard. So all we need to do is we just adjust the instrument based on the signal. And it's one thing that we could say an error-proof technique. Okay, so that's why every time we run the instrument in Raman, we always, that's the first thing that we do to make sure that we can at least follow where the signal is. Okay, so yan yung spectrogram, and you rarely use it. Okay, now the one that you can include here is the instrument that you usually have. That's a spectrometer. So this is a spectrochemical instrument which employs a monochromator or a polychromator. So I think this is the one that you have here. Okay, so here you just have one here, and here you have more than one. Okay, and what it is, this is in conjunction with the photoelectric detector of the isolated wave band. So lahat sila, meron kang photoelectric detector, photodetectors here. Doon, meron kang plate or array detector. Okay, so these are, we could say, the typical thing that you have, whether you have AAS, whether you have fluorescence, chemiluminescence, okay, or the typical UVBs. Okay, so if you have what we call a spectrometer, so usually you have here a photodetector that is placed outside nung tinatawag nating exit slit. So this is the exit slit. So you have a photodetector there. So if you have a polychromator, okay, so you have several exit slit. So the instrument is usually called, if you have it like this, several detectors, we could say this is a direct reading spectrometer. Now, some spectrometers, they use optical components to sweep, okay, the spectrum quite rapidly across a single exit slit. Now, these rapid scanning spectrometers can obtain spectrum. So usually, kaya nilang magbigay sa'yo ng ganito. Okay, but usually, this one, maybe like AAS, you only have a particular wavelength. Okay? So yan yung spectrometer. Mamaya, meron pang ibang term, spectrophotometer, spectrometer. Hindi pa magkatulad yan eh. Okay? Now, if we're going to talk about here sa spectrometer nga, we have the monochromator and the polychromator. So, sa monochromator, yung exit slit natin is about the same size as the entrance slit. Okay? And it is used to isolate a small band of wavelengths from all the wavelengths that strike the focal plane. Ano kaya mangyayari kung hindi sila magkaiba yung size? So, if they don't have the same size, okay, yung radiant or yung power, yung light na mapapasok mo, hindi siya, because it could affect the input-output thing. So if the input has lower or smaller size compared to the output, okay, hindi maganda yung pagkukuha ng signal. So as much as possible, you put this the slit size at the same one. So it's 2 cm pareho, 4 cm pareho, or 1 cm pareho, as much as possible. Okay. Now, where do you see this one? Sa UV beams, tsaka saan? Yung monochromator. Usually, we could say yung slit, they play a very important role mostly dito sa fluorescence. Okay? So, what happened here? In the monochromator, usually ilan yung band mo? Ilan yung wavelength band mo? Usually, you only have one wavelength band. So what you could do, okay, if you have a monochromator, you have one wavelength band at a time, okay? Ina-isolate mo to, and different wavelength bands, okay, can be selected sequentially by rotating yung dispersion element. So remember, if you're going to look at the thing here, isa lang yan. Isang band lang yung makukuha mo. But, by rotating this, pwede kang makakuha ng iba't ibang wavelength. Okay? So, meron kang mag-aano dito, yung pang-rotate. And it will generate different, what we call wavelength. You rotate mo yung dispersion element mo. And they will bring new band into the proper orientation so that, okay, it will pass through the exit slit. Have you looked at inside the instrument? Yan yung ano namin ni Sir Mikor noon eh. Sabi namin, okay lang hindi mag-work yung instrument. Tapos babaklasin namin and you will see the mirror system that they have inside it. I don't know if you have experienced that. Okay? Usually, ano namin pag sira na yung, yung instrument. Kasi pag nag-work pa, ayaw namin buksan. Bakit? Pero sa US pwede. Pero dyan sa Pinas, ayaw namin buksan. Anong problema? Kapag iniwan mong bukas yung instrument, I mean, yung tinanggal mo yung casing niya dyan sa Pinas. Ewan ko, sobra yung ano dyan. Pero dito, iniiwan namin bukas, okay lang. Okay? Yun yung isang observation namin. Diyan, konti ano lang, alikabok na. Wala, hindi ata ako nag-record. Nagre-record. Akala ko hindi ako nag-record. Okay? So, if you open the thing, the casing, you remove it, you will see some of the mga mirrors lang yan eh. Yung dispersing element na yan. Okay? And it's all like that. You can even construct your own what we call instrument. Do you know Dr. Tapia? Alvin Tapia in physics? I think nagko-construction ng mga yung ganito. spectrochemical instrument. Okay, all you need, if you're fond of electronics, you can do it on your own. Pinakita sa inyo yung bukas na, at least may natuto siya sa amin ni Sir Mix. Because the instrument that we have before is almost not working. So, ang ano namin, binubuksan namin and to see how it works out. Even here, minsan, kahit yung laser, pinapakita ko sa mga bata last time sa AAS, sabi ko, as you could see here, you could see some light passing through sa IR. Sabi ko, ayan, makikita nyo. Tapos sa fluorescence, we have to turn up the light so you could see that when they put something fluorescent, makikita nila yung light, okay, coming out of it. Okay? Now, if the focal plane contains multiple, we could say, exit slits so that several wavelength bands can be isolated simultaneously. So we call the wavelength selector as polychromator. Okay, so ang pagkakaiba nito, this is a mono, okay, and this is a polychromator. Okay, so yan yung we could say way to select the wavelength. Okay, and then ito pa, spectrometer versus spectrophotometer. Ano yung pagkakaiba nila? Tapos meron ka pang tinatawag na photometer. Meron na ang spectrophotometer, meron ka pang tinatawag na photometer. Okay? So, ano yung spectrophotometer kaysa doon sa spectrometer? So, yung definition natin ng spectrometer is spectrochemical instrument which employs a monochromator or polychromator in conjunction with photoelectric detection of the isolated wavelength mass. Now, if you have a spectrophotometer, okay, this is just an instrument similar to the spectrometer, except that it allows the ratio of the radiant power of the two beams to be obtained, a requirement for absorption spectroscopy. Okay, so we could say spectrophotometer is also a spectrometer, but it only measures, okay, the intensity of your light. Based on this, allows the ratio of the radiant power of two beams to be obtained. Now, yung photometer, okay, is a spectrochemical instrument which uses, meron kang tinatawag na optical filter for wavelength selection in conjunction with photoelectric detection. Okay? So, is this the first time for you to hear this? Yung difference nila? Pwede kaya natin sabihin na a spectrometer and a photometer will give you what? Ha? Pwede kaya ito plus spectrometer will give you what? Yan. So if you're going to look at some readings, spectrophotometer in general consists of two devices. Yung tinatawag natin spectrometer and photometer. Okay? So yung spectrometer, the device that produces or typically disperses and measures light. Yung photometer mo naman, it indicates the photoelectric detector that measures the intensity of light. So here you can see it just uses an optical filter for wavelength selection, okay, in conjunction with the photoelectric detection. Now here you could say allows the ratio of the radiant power to be obtained, Yung spectrometer naman, if you're going to look at definition here, okay, it employs a monochromator and polychromator in conjunction with photoelectric detection. So pag pinagsama mo yung pareho, meron ka ng tinatawag na spectrophotometer. Okay? And then meron pa to. Meron tayong tinatawag na interferometer. But we don't use it in UVBs, usually around IR. That's where you have it because interferometer is a non-dispersive devices in which the constructive and destructive interference of light waves can be obtained okay, can be used to obtain spectral information. So you're familiar with the constructive and destructive. So parang merong ganon. Tataas lang, di ba? Tapos yung isa naman pag ganon, tapos ganon, ano mangyayari? Magka-cancel out lang or mawawala. Yan yung constructive and destructive interference. So usually interferometers, if I'm not mistaken, you use it on IR instrument. Okay? So what we're trying to do here, what we're trying to do here is we just want to measure yung tinatawag nating optical signal, optics. Okay? So when we're talking about optics, this is the light. Usually interaction with what? Pag optics ka. Anong usually kapag tinatawag na optics, anong involved dyan?
UVs.
Okay? So usually optics, di ba, I need, anong chem yan? Anong physics yan? Kasi part yan ng physics eh. Anong ini-study ng optics sa physics? Behavior of your light.
Light. Mm-hmm.
Yeah? Doon kapag ano ka sa optics ka, it's just a branch of physics that studies the behavior and properties of light, including saan pumapasok yung chem. Kapag ginagamit mo yung light sa pag-interact sa matter. Okay? So optics usually include the UVBs, the visible, and the IR region. Yun yung ano ng optics. It's a very good field in what we call in physics. Okay? That's why I told you, kung gusto mo mag-construct ng instrument, it usually involves more physics and some engineering. Okay? Kasi transducer yung kailangan mo is how to obtain signal. Once you can do that, you can use what we call, you can develop any sensors or detectors depending on the physical property or chemical property that you can get. Okay? So when we're talking about the optical signal measurement, we could say all spectrochemical techniques that operate in the UV, visible, and the IR regions of the spectrum employ similar instrumental components as mentioned before. Okay? And the major instrumental difference could be between emission, photoluminescence, and absorption techniques that occur in the arrangement and type of sample introduction system, encoding system, and the information selection system. So how you introduce the sample in the system, how, okay, the transducer or the encoder convert, okay, the concentration that you have there into optical signal, which in turn is converted to electrical signal, and from the electrical signal, how it can be translated into a readout system that is understandable by the user. Okay, so all techniques depends on the measurement of the radiant energy or radiant power. Lahat yan. Okay, you don't have a light source, you don't have any spectroscopic methods. I think that's one and the most important part. Okay, Sometimes you don't even need a detector, okay? But what do you think happened if you don't have, let's say, a detector or a readout system? What would be the basis of your analysis? It's all what? Qualitative, right? Do you agree that you don't need, if I ask you what is the most important parts in a spectrochemical system, and my answer is, we could say, light source. Okay, without the light source, okay, the readout system is useless, the encoding system is useless, because without them you can still analyze the sample. The only thing is it's limited to just what? Qualitative method. Kasi if you want to see if a material is fluorescent, all you need to do is shoot light and see if it fluoresces. If it doesn't fluoresce, then you could say that there's no light on it. Okay. The other thing is just to improve the detection. Okay? If you want it to convert into a quantitative method. Okay. So the specific transducer and signal processing device used in various regions of the spectrum in specific electrochemical techniques are going to be described later. So chapter 3, I think we're going to go on each part of them. At least dito sa chapter, titingnan lang natin yung signal na extracted from the readout data doon sa spectrochemical system. Okay? So for instance, here, usually ganito yung simple block diagram of any spectrochemical method. Okay? So as I've told you, if I ask you which do you think is the most important part sa apat na yan?
Light source
Light.
po.
This one. Kasi pag wala yan, hindi to gagana, hindi to gagana, hindi yan gagana. And even if this one are not present, you can still analyze. All you need to do is shoot the light source to your sample. Sometimes we have to look at it directly, especially with dealing with laser. Sabi namin, kaya na kaya to? So we turn off the light and then shoot the thing here. Yes, you have to use a special mask because you don't want your eyes to be destroyed by the laser. Even if it's a monochromator, there are still some other wavelength of energy that's coming out there. Okay, but this is what you have. So what happened here, your radiant power monitor, okay, it provides a numerical readout, okay, that is related to the radiant power. So the way that you're going to look at here, especially if you're using high energy source, you have to make sure that it will not destroy your sample. Okay, so you have to determine the number of photons per second, or the watts, when you hit the so-called transducer. So the radiant power monitor provides a numerical readout that is related to the radiant power, okay, impingent on the transducer. Okay, so here we can look at the so-called analytical signal. Okay, and just like everything, the analytical signal that you have is rarely obtained directly as a result of one spectrochemical measurement. Hindi yan yung tipo pag ano mo ng sample, lalabas agad sa'yo, okay, yung information na kailangan mo. Okay, so it depends on the methods that you use. So because of the presence of what? Why do you think it is hard to obtain directly the signal or the analytical signal? Ano yung pwedeng mag-interfere sa signal mo? Ha?
Yung matrix, sir.
Yung matrix. And it will affect what? The background. The presence of the background and other extraneous signals that I'm going to discuss. Okay. What happens is your analytical signal must be extracted from a raw readout data. Okay. So depending kung ano yung method mo, may definition yung analytical signal mo. So if you have emission and chemiluminescence technique, you can define the signal to be displayed by the readout device due only to analyte emission. Okay, and it is usually given by the symbol EE, and we presume that EE is directly related to the radiant power of the emission, power of E here, the IE here. Okay, and similarly, yung analytical signal ng photoluminescence techniques, you use this one. Okay, this is the this one is term of energy, and this one in terms of luminescence. So this is the measured signal due only to radiationally produced emission of the analyte. So at least we could say in emission, chemiluminescence, and photoluminescence, the signal is just due to the analyte that you're looking for. Unless fluorescent din yung present materials doon. Okay lang kung yung fluorescent doon ay yung analyte na inaano mo. What if you have contaminants that also emit or fluoresce at the same wavelength as your what we call analyte? Okay, but it's rare. Okay. In the case of the absorption methods, the analytical signal is the absorbance due only to the absorption of radiation by the analyte species. So you want to make sure na yung analytical signal mo ay galing mismo doon sa analyte. Okay? Now, what if yung signal mo hindi galing sa analyte? Anong tawag mo sa signal na yon? Ito yung tinatawag nating extraneous signal. So the background or the extraneous signal, okay, they registers on the readout device due to the two sources. Okay. Now, the presence of these extraneous signals is common. Why? These signals can come from what? Yung term na natutunan natin dito, yung concomitants. Okay? Saan pa? Ano pang pwedeng source ng extraneous signal nyo?
Ray light, sir.
The light, yung room light. When we do Raman, meron kaming dark room. Tapos meron kaming parang switch na nakaano. Tapos ang ano nga namin, kailangan nagbi-blink yung sa pintuan ng room. Okay? Mamumura namin kung sino yung nagbukas ng ilaw because it can destroy the detector. Ganun ka-sensitive yung detector. Okay? Because we want the signal that is going to be obtained by the detector to be coming from the sample that is being hit by our laser source. So kapag nag-open yung light, pwedeng matanggal yun. Okay? Or it will give other source of energy that can destroy the detector. Saan pa? Aside from light, ano ba usually saan mo nilalagay lagi yung sample mo?
Scattering po dahil sa cuvette.
Okay? Scattering. Okay? Or di kaya yung sample cell. Especially if it's fluorescent. Okay? We usually put our cuvette in what? Nitric acid. I don't know if you could see it. Hindi ko, ewan ko kung kita niyo yung aking parang ano, souvenir. Nung grad school ako, I have some nitric acid spill. Naka-gloves ako. Tapos nag-aano ako ng cuvette. Nag-spill sa akin. Kasi alam niyo yung wash bottle? So, meron kaming wash bottle doon sa na naka-contain ng nitric acid. Nitric acid yung pure. Because what we do is to make sure na yung cuvette namin clean, kahit na ang dami naming cuvette. Okay? So, one day, I tried to do it. Nag-spill sa ano ko. Ewan ko kung kita niyo yung parang peklat. Oh, parang talagang sagad sa buto. Na-feel ko yung, na-feel ko yung pain. I have like this one. So, hindi masyadong nasarhan nung sino man gumamit. So, nung pagkaano ko, lumampas dito sa akin. And it really hurts. Until now, meron akong souvenir. Okay? Because we put nitric acid to that. It's a strong oxidizing agent. So, lalo na yung mga fluorophore, okay, na materials na nalagay dun sa cuvette, matatanggal siya. Okay? Because if you leave something there, especially if you're using fluorescent, talagang mag-i-interfere doon sa sample mo. Okay? Mag-ano siya ng tinatawag nating extraneous signal. Okay? So, you usually get two signals when you do this spectrochemical analysis, yung extraneous signal tsaka yung analytical signal. Okay, and in these analytical signals, sa extraneous signal, you have two primary sources. The first one is the so-called dark signal. Okay, so in this first source, which is the dark signal. So the dark signal of the radiant power monitor, which is the signal present when no radiation is impinged on the transducer. So nandun na siya. Okay? Kahit wala kang inalagay na what we call radiant energy, it will give you a signal. So we could say that's the noise that you have there. Okay? And the second one is the background signal. So this is due to the background radiation that strikes the transducer. And if you have the background radiation, okay, this is composed of the radiation from all sources other than the desired optical phenomenon from the analyte. Dito na ngayon pumapasok ng tinatawag natin mga cosmic rays. Because cosmic rays, if you're going to look at the electromagnetic spectrum, it is wonder. Even I am still wondering, ano naging cosmic rays to? Out of nowhere. But we always say, what is that signal? Okay? At least, kapag meron kang fluorescence, meron kang tinatawag na Rayleigh scattering, we can consider that as a background radiation or a background signal. Okay? So, how do you remove this background or extraneous signal? You use yung tinatawag nating blank. So usually, pag sinisiro mo siya, yan yung gagamitin mo. But sometimes you cannot zero it. So what you do is you're going to get the signal, like it is a sample. Pwede ka lang mag-zero saan? Sa absorbance, right? Because what you do is you set it, so let's say blank muna. So ilalagay mo yung blank mo. And then to test if it's what we call working, kukunin mo yung signal using the sample. So if it's good, it should be what? Like this. I remember last week when we did the UVBs. So pag sinisiro ko, ayaw mag-zero. Eh since one wavelength lang siya, sabi ko sa mga estudyante ko, just get the reading of your blank as is. And then you subtract it kung ano man yung reading ng sample mo. Eh, person nila, no, it should be zero. Yeah, it should be, but the instrument won't zero. Okay? Siguro kasi ano lang siya, yung one wavelength lang, hindi siya yung spectra. Kasi yung spectra pwedeng mag-zero agad eh. Pag isang wavelength lang, tinatay namin zero ayaw, talagang mga 0.025 yung lumalabas. So sabi ko, record that, and then what we call subtract, okay, whatever the sample, whatever the reading of your sample is. Okay, so let's look at the signal that we get from the different methods. So we have here instrumentation for the emission electrochemical techniques. So you have here the excitation source, the sample container, the wavelength selector, and the radiant power monitor. Okay? So, dito sa excitation course, pwede natin ilagay dito yung encoder. Okay? Ito yung tinatawag natin excitation source is the spectrochemical encoder. Why? Bakit siya yung tinatawag nating encoder? Because some samples, okay, will just excite as a certain wavelength. So pag mali yung excitation wavelength dito, yung source, mali yung makukuha mong tawag dito light source. Okay? So the excitation here, this is just similar to what? Absorbance. But in the excitation here, okay, being the spectrochemical encoder, the right excitation source, when applied to your sample container, will generate what? Some emission or chemiluminescence. Okay, so the emission that results from the excitation of the analyte species by a flame, plasma, or chemical reaction encodes the concentration of the analyte as the radiant power of emission. So usually the way that you're going to do is you're going to collect it at a specific wavelength. What do you observe when you use spectropolarimeter? Dalawa yung lambda mo, di ba? Ano yung isang lambda? You have an excitation wavelength and
Emission wavelength.
emission wavelength. So the excitation wavelength refers to this, the emission wavelength refers to this. I-excite mo siya at a certain wavelength, tapos i-collect mo siya at a certain wavelength. Alin usually yung mas mataas yung energy? Lambda X or lambda max? Or lambda X or lambda M?
Usually yung excitation po, sir.
Okay. And this is usually in the shorter wavelength. Because this is more powerful. Doon sa emission wavelength, tinitingnan mo lang kung ano yung na-emit. And for it to be emitted, you need to have a high energy to excite. Okay? So in some spectrochemical methods, the excitation source and sample container are an integral unit, as in the nebulizer or burner used in flame emission. Meron tayong FES, flame emission spectroscopy, or FAES. Okay? Or yung reaction cell na ni-use sa luminescence. So if we're going to look at the electrical signal of the sample, it's usually what? The composite signal, like ETE. So this total signal is the sum of the analytical signal, the dark signal, and the background emission signal. Okay? So if we're going to look at this one, we could say ETE, that's the emission of the total emission that we have there. So this is equals to what? Sabi ko nga, EE, ED, and EBE. So ito na yung kasama yung tinatawag nating extraneous signal. Ito yung analytical signal. Okay? Now, to extract the analytical signal, a second measurement is required to obtain the sum of the dark signal and the background emission signal. So this second measurement is normally made with replacing the analytical signal with a blank. So mangyayari nito, yung EE mo is just equals to ETE minus EBK. Ano tong EBK? Yan yung blank signal. Yan yung total ng dalawang to. Now, usually embedded na yan doon sa instrument. The dark signal can be obtained separately by blocking all radiation from reaching the radiant power monitor. And the background emission signal could then be obtained from the E of this background signal minus the E from the dark signal. In many instruments, the blank solution is used to adjust the readout device to read 0 by suppression of the blank signal. So dyan yung pumapasok yung use ng blank. Okay? So this establishment of zero's position is still, however, a measurement of the blank signal. So talagang important yung blank. Okay? Kasi kapag wala yung blank, everything will just be, oh, hindi mo alam na meron doon contribution coming from the blank. Yung problema namin sa emission, lagi yung water. Laging may relay scattering. Tapos pag fluorescent yung sample mo, okay lang, ganun. Minsan, pag weak yung fluorescent niya, mas weak din yung yung tawag relay scattering mo, tapos may ganito. So kapag sinabtract mo siya, ano mangyayari? Ganito. So what's the best way for you to do? Let's say kung ipa-publish mo to, ipapakita mo bang buong to? Ano gagawin mo? Usually kinakat namin. Tapos ito ipapakita namin. Okay? But usually the case is this one. But there are cases when I work with tetracycline. So ganun yun sa water. Taas. Tapos yung ko, weak, meron siyang weak ka. So weak din yung niya. Meron din ganun. So sabi namin, paano yan? Pag sinabtract mo, merong pababa. So said, cut it. Ito lang pakita mo. That's allowed because you know that the component that you have there is the difference is just the sample that you have, the analyte that you have. Okay? So this is emission and what we call chemiluminescence. Paano naman yung photoluminescence spectrometry? So here, you have a radiation excitation source. So we could say this is your external source of electromagnetic radiation. And what it do, it excites the analyte. So mag-aano ka, select ka ng wavelength na mag-excite doon sa analyte na nasa sample mo. So the analyte concentration is optically encoded as the luminescent, okay, radiant power. So meron kang parang ganyan. Okay? And this is measured with the radiant power monitor. So ito lang usually yung taga-measure niya. Okay? So the emission wavelength selector that views the luminescence of the sample is typically placed to collect radiation at 90° with respect to the excitation axis. I think the fluorescence is more here compared to the one that we have here. I think this is more on the AAS. Kasi usually excitation source mo, excitation source mo sa AAS yung plane. Okay? You put the sample and then you look at a certain wavelength kung ano yung element na gusto mong tingnan. Okay? So this is more on the fluorescence that you have here. So the specific wavelengths from an external radiation source are isolated by the excitation wavelength selector to excite the analyte in the sample cell. And then the emission wavelength selector selects the wavelength band where your analyte fluorescence is concentrated and passes it through the radiant power monitor. And if you're going to look at how the signal comes here, sa atin kasi sa 137 lang, signal. Yung pagkakaiba pag grad force, yung parang into detail ka. So yung total analytical signal mo is ito. Okay? So ito yung analytical luminescence signal. Tapos ito, ano tong EE na to? Okay? You have the analytical thermal emission signal. Tapos ito ay yung blank. Okay? And if you're going to look at the blank, you have here, this is what? The dark. And this is the background. Ano tong isa? Ano yung tasing yung SC?
Scattering.
Scattering. Tapos ito, ano yan? BL na yan. So you have the blank luminescence. So analyte and background emission in the UV breeze region are usually significant only in atomic spectroscopy. Okay?
Ano po sir yung source ng E sub E?
Alin?
Yun ba yung
Is-
mga radiationless relaxations po ba?
Oh, yung mga yun nandyan. So the analyte luminescence signal can be obtained with two measurements. Only if the analyte emission signal EE is small compared to the what we call the luminescence, which is often the case. Now, if the analyte emission is significant, subtraction of the blank signal gives a measured analyte luminescence signal that differs from this one. So meron pa yung E sub luminescence, and that is equals to the luminescence signal plus yung analyte emission signal na meron ka. But to obtain the true analyte luminescence signal, EL, when EE is significant, the excitation source must be turned off. So doon mo makikita yung what we call EL. Okay, then the two measurements of ETE are made to obtain the EE. Now, subtraction of the EE from EL gives the true analyte luminescence signal. Now, in some cases, it's possible to eliminate the measured contribution from the analyte emission optically or electronically. So example nito, kapag yung excitation source mo is modulated and you use AC amplification, the AC luminescence signal can be distinguished from the emission signal. And often the black measurement is set to the zero position of the device. So usually kapag meron kang re-zero, yun na lang yan eh. Pag may blank ka, pindutin mo na lang yun. Tapos kung ano man yung signal na makukuha mo, yun na rin yun. Okay? That's the simplicity that we have right now with the advent of this what we call instrumentation. Hindi tulad noon, you have to get everything blank, tapos do lahat raw data. And then you have to do the calculation. Okay? Now, the typical absorption spectrometers, you have a radiation source, you have a shutter, then a wavelength selector, you have the sample, and then another wavelength selector, and then the radiant power monitor. So we could say this is similar to the luminescence spectrometer, except that all components are placed on the same optical axis. If you're going to look at the other one, may paganito. Sabi ko nga, merong L, sometimes merong kang T. Okay. Now, the shutter, what do you think the shutter do? Ano yung use ng shutter? Wala. Kasi yun yung kakaiba kaysa doon sa mga nauna. Okay? What the shutter do is allows the user to block the radiation source in order to obtain the dark signal. And usually in the wavelength selector, you only allow one wavelength, okay, required. Now, absorbance measurement can be made as what? Ano yung T? Transmittance. Where absorbance A is calculated manually or the logarithmic concentrations can be done electronically or with the computer software, and the absorbance A is displayed on the readout system. If you're going to look at the old spectrometer, what do you see? Meron kang makikitang ganyan, tapos merong percent transmittance, tapos yung absorbance sa baba. Okay? So usually, ano yun? Pag 100 dito, ano equal dito? 0, di ba? Tapos pag 0 dito, around what? 2 something. Okay? So makikita mo yan sa ano? Sa mga old instrument. Okay? And right now, all you need to do is what? Put the blank. If you can zero it, and then put this sample, and then you get the absorbance. You rarely get the transmittance. Okay? So the transmittance value could be obtained by measuring the ES. So what is ES? S stands for sample. That results from the source radiant power passing through the analytical sample. Okay? Or measuring the signal ER. R is reference. That results from the source radiant power passing through the ideal blank or reference solution. Yan yung tinatawag natin kapag meron kang double beam. Buhay pa yung double beam natin yan.
Hindi ko lang sure, sir.
Nagamit niya sa 137.
Opo. Buhay pa po ata, sir.
We have a double beam also here, but we rarely use the reference here. So what we usually do is we put the blank here, tapos i-run as blank, and then i-run mismo yung blank as sample. Pag 0 na yung signal, so yun na lang gagamitin namin. Because if you have a double beam, hassle kasi yung extra cubet na naano doon when you can use that extra cubet for other samples that you have. Okay. So once you have that, you have the ER and the ES, then you can get the transmittant. Okay. So the signal coming from the sample over the signal coming from the reference. So in practice, the presence of the other signals like dark signal program necessitates a third measurements. At yung third, yung measured transmittance na yun is defined by this equation. So ST, okay, over RT. So ano yun to? Meron kang tinatawag na 0. Like a reference that you have there. So EST, we could say, I think I still have here, the total sample signal obtained with the source shutter open and the analytical sample in the sample container. The EOT, that's the 0% transmittance signal obtained with the shutter closed. So dyan pumapasok yung shutter. But right now, you don't use the shutter anymore. Remember, this book is what? Written in 1988. So during that time, ito yung high-end na instrument. But the principle that they have is still based on that one. So ngayon, lahat in-automatic na lang nila. So naka-incorporate na yan doon sa instrument na ginagamit natin. Okay? So yung ERT na doon, meron kang sineset na 100% signal obtained with the shutter open and the blank reference in the sample container. Hassle yung may shutter eh. Kasi meron kaming fluorescence na may shutter. So minsan, hindi mo alam kung open or closed. So kapag close siya, pag kinuha mo yung ano niya, yung reading, wala kang makikitang signal kasi naka-close yung shutter. Now kapag open naman, ayaw mong buksan yung sample compartment mo kasi lahat ng light pupunta doon, so madadali yung detector mo. So the shutter that I have experienced, hindi na ako naka-experience ng shutters absorbance, but I still use it in an instrument, in a spectropolarimeter. And hassle, even the students hate it. But I said, what can I do? That's how Hitachi yung company. Okay. And then if you have E0 signals, that refers to EOT. It's composed of any background emission and dark current. Okay. So E of this, what we call 0T equals to E minus the blank, okay, plus the dark signal that you have. And when the blank is in the sample container and the shutter open, the total measured reference signal, ERT, is called the 100% transmittance signal, and it's composed of the reference transmission signal, EI, okay, the 0T signal, and any background illuminescence, EBL. Kaya sinulat ko lahat dito. But you rarely, what we could have that right now, because it was already incorporated in the instrument. Okay, na lahat ito ay nandoon na. Okay, so when the analyte sample is in the sample container and the shutter is open, the measured signal is EST, the total sample signal, and this is given by this. So this is the sample transmission signal. This is the emission signal. This is the luminescence signal. Okay. And these are the background luminescence, and this is the one with zero transmittance. And if you're going to look at the equation, yung measured transmittance mo ito. So good for you. Simplify na lahat. So you could just imagine how they're working with this instrument before. Kukunin lahat nila yan. And that's for reading. So after one day, inok mo, gawa ka na naman ng panibagong reading. Right? Especially now, you still get the signal in every reading. Some would say, can we get this? Can we get the blank every time you read? You can say yes. Okay? Because that's the right one. Okay? So we can have the direct absorbance readout, wherein the true absorbance is given by A is equals to the voltage proportional to the absorbance, or K, wherein the log conversion factors in volts per unit. Ano yun? Time na malapit na yung ano. Okay. Now the voltage EA and hence here are found from two measurements. So yung reference na meron ka, yung absorbance reference logarithmic voltage or zero absorbance, that's voltage EIR, is obtained with the shutter open and the blank in the container. And then the sample logarithmic voltage is obtained with the shutter open and the analyte sample in the container. Okay? So yan yung, we could say, true absorbance readout. So yung direct. Okay? And if you're going to look at the voltage, you can look at this one in terms of this. Hindi ko na aanuhin. Okay? Because we're almost out of time. So the transmittance one and the direct absorbance readout. And most of the time, I would say this is the one that we use now. You rarely see transmittance in the reading. Okay? So it's all based on this one here. So that's what we have for now in the two chapters from Engel. Ipopost ko lang, I mean, you got the message in the chat, the Facebook chat, about the link, if ever. Okay? So siguro by next week, mag-start na tayo ng quiz. Kasi dalawa na yung chapter na naano natin eh. Natapos. Okay? And I might, by next week, post some questions for you. Isang midterm, isang finals na take home. as usual. So imagine if they still have this signal. Ano kaya gagawin yung research? Ngayon, what do the instrument do? So sometimes they already take care of this background signal, and then in addition, pwede pa silang maglagay ng software na pwedeng panggamit sa pag-process ng data mo. Okay? So sa IR, I remember in the IR, pwede ka na mag first derivative or second derivative if you have the software Omnic that is usually installed with Thermo Fisher IR instrument. Okay? Yung noon origin na ginagamit namin sa Fluoromax, ngayon, okay, you can do PCA. That's the same what we call the software that they have. So talagang everything's becoming so easy. Okay? So imagine working this maybe 70s, 80s when the book was written. So everything they have to do, it's a lot. Okay? Parang in-imagine nga namin yung nag-a-assay kami sa antioxidant. So we have to get it before 1 cubet at a time. And then I didn't realize 2 years while we're doing that, we already have the microplate reader. And I didn't realize that, oh, can we use that for that? So lahat kami nag-ship doon. So that's how technology has what we call improve the instrumentation. Okay? So talagang we are in a much better one. Anong bago dyan sa IC na instrument? Aside yung kay Ma'am Peralta.
Yun lang po yung alam namin, yung kay Ma'am Peralta.